Hi. Before starting section 7.6, which is complex eigenvalues, and let me classify the eigenvalues, okay? First of all, in the previous section, which is 7.5, we talked about the all eigenvalues are real and different from each other case, okay? And then like in section 7.6, we're going to talk about the complex conjugate pair as your eigenvalues. And in section 7.8, we will talk about repeated eigenvalues. Okay, but this discussion is the same thing. So we already have an idea about which one. Let me try to summarize it. Okay. Same thing with different case, right? We just set it to the minus lambda into the lambda t form as your solution, then we could get a like the solution of the system of differential equation, right? And then the second case, whenever we have like complex conjugate pair, and your solution, I mean like the fundamental set of solution will be the like an exponential function times cosine and I sine function form. Okay, and we're gonna take the like e to the lambda t cosine and e to the lambda t sine as the like the fundamental set of solutions. Okay, and repeated eigenvalue, it is similar idea with chapter 3. Okay, we will talk about step by step. Okay, so let's start 7.6. Okay, since we have an idea, like it might be better to talk about this one with the example. Okay, here we go. Again, section 7.6. Where am I? There we go. So I have made this form of differential equation. Then we're going to try to find the fundamental set of solution. Okay, and the process is same. We're going to start from eigenvalues. Then we're going to find the corresponding eigenvectors. Okay, here we go. So to find eigenvalues, we're going to set determinant a minus lambda I equals 0. Okay, plug in everything. It is minus 1 minus lambda, 2 minus 2 minus 1 minus lambda. Well, actually it's determinant, right? Which means minus lambda times minus 1 minus lambda, which is minus 1 minus lambda squared, and plus 4 equals, okay, minus times 2 times minus 2, right? So which is 1 plus 2 lambda plus lambda squared plus 4 equals 0. Let me write in order. Lambda squared plus 2 lambda plus 5 equals 0, okay? And unfortunately, there's no way to factor this, guys, this equation, but we can use the quadratic formula, okay? Then here we go. My lambda is equal to minus b plus and minus and square root of b squared minus 4 ac over 2a, okay, which is equal to negative 2 and plus and minus square root of minus 16 over 2. Simplify a little bit more, equal to negative 2 and plus and minus 4i over 2. So your lambda is negative 1 and plus and minus 2i. Okay, so let me, that's it. Okay, so I can say this is the complex number pair. Okay. Well, okay, what I will tell you is this one, okay? Well, in the previous problem, you have like two different real values, and we had to find the corresponding eigenvectors for each eigenvalues, okay? But for this case, you don't have to do both of them. Just one of them is fine, because like if you do like the other one, you will get a same set of fundamental, same pair of the fundamental solution, okay? So let me take only one of them, okay? Here we go. corresponding eigenvector, okay? My lambda is equal to -1 plus 2i. Again, you don't have to worry about the minus or minus 2i case, okay? So then to find eigenvector, and you need to set up a minus lambda I v is equal to 0, right? Plug in lambda, then your a minus lambda I is -1 minus +1 minus 2i. Can I just like this way? Is it okay? And 2 and -2 and -1 plus 1 minus 2i. I just subtract my lambda and let me write as a vector form and vector 0. That's it, okay? Then simplify is -2i, 2, -2, and -2i, and v1 and v2 equal to 0 and 0, right? So from this guy, and we can easily conclude like this way, -2i v1 plus 2v2 is equal to 0. Then when I divide by 2 and move I vi to the right hand side, then I can say v2 is equal to I v1. Okay, if I say your v1 is 1, then your v2 is I. Okay, then we can say that is your eigenvector. Okay, there we go. So finally, my eigenvector is equal to 1 comma I. Is okay, which is complex value eigenvalue or eigenvector, right? So okay, like from this point, let's do the same technique with chapter 3. Okay, here we go. I need more space. Okay, so now since my eigenvector is like I1 comma I, then we can write the solution. Okay, here we go. Then my solution is, okay, here we go. X1 is equal to e to the my eigenvalue, which is -1 plus 2i, right? -1 plus 2i t, then eigenvector. Okay. Then do you remember Euler's formula? Okay. We're going to apply the Euler formula for here. Okay. That can be written by. Okay. Let me rewrite this one more time. Okay. This guy is equal to e to the. Let me rewrite this one in terms of real part and imaginary part separately. Okay. E to the minus t and plus 2t and I. Okay. Just want to show you like it is imaginary part. Okay. And 1 and I. Then this part, Euler's formula, okay? Okay, which is, let me write the Euler part with a red pen, okay? It is e to the real part is just real part, but imaginary part will be written by cosine 2t plus I sine 2t. That's exactly what I did in chapter 3, right? And 1 and I, okay? Then okay, this guy can be written like this way as a vector form. I'm going to multiply whole red part to the like a vector 1i, okay? That is e to the minus t cosine 2t plus I sine 2t. And the second part is I times e to the minus t cosine 2t plus I sine 2t. Is okay. Now let me try to separate your real value part and imaginary part. Okay. This guy can be written by e to the minus t cosine to the, which is like a real part. And what about imaginary part? Plus I times e to the minus t sine 2t, right? What about second one? Like since like you're gonna work by I, let me write the real part first. Okay, real part came from I sine 2t because you're gonna work by I, right? I times I is -1, so your real part is minus e to the minus t, and sine part is your real part now, okay? Then imaginary part is I e to the minus t and cosine 2t. Okay, now let me separate this vector as like two separate vector with the real part only and imaginary part. Okay, so this can be by like this way, e to the minus t cosine 2t and minus e to the minus t sine 2t, and plus with I e to the minus t sine 2t and e to the minus t cosine 2t. Is that okay? But please keep that in mind. Even like these two separate vector came from only one eigenvalue and eigenvector, but like, keep that in mind. It is a linear combination with like two different vectors, right? Because I is constant, okay? Does it make sense? So we have to verify, and these two vector forms the fundamental set absorption, okay? So let's say this guy is U1t, and this guy is U2t. And I'm gonna show like U1 and U2 form a fundamental set absorption, okay? Does it make sense? So how can you check it? It's really, first of all, you have to double check like these are really solution of differential equation, okay? So how can you do it? As we practiced it before, we're gonna plug in back into the system of differential equation with like this two vector U1 and U2 that you have to verify it satisfy the system of differential equation, okay? It is true, okay? I'm gonna skip this one, but like it is very true. But second one, we have to verify these guys are independent, right? How can I do it? And that's really simple. It is Wronskian, okay? We're gonna check the Wronskian is not equal to 0, then we can say this two vector, which is U1 and U2 form a fundamental set solution for this system, okay? So let's do it, okay? Here we go. So Wronskian. There we go. We need more space. Can I make it a little bit smaller? If you don't mind, please. There we go. Now I have enough space. Let me check the load scale, okay? Here we go. Okay, so well, since this is a vector, we can set as the matrix, combine the matrix, and the Wronskian is exactly the determinant of the matrix, right? So here we go. E to the minus t cosine 2t and e to the minus t sine 2t minus e to the minus t sine 2t now and e to the minus t cosine 2t, right? So that is equal to e to the minus 2t and cosine square and minus plus e to the minus 2t sine square, 2t, which is equal to e to the minus 2t cosine square 2t plus sine square 2t. And as you know, this guy is the trig identity, which is 1. That is equal to e to the minus, as I told you, exponential function never be equal to 0, okay? So we can say this is not equal to 0, which means your Wronskian of u1 and u2 is not equal to 0. Then my conclusion is u1 and u2 are a fundamental set of solution. Okay, so like by the superposition, your solution system of differential equation is the linear combination of u1 and u2. That is the conclusion of this one. Okay, that's it.